F be a continuous function for all real numbers with an inflection point at x equal to a, which statement must be true? So probably a lot of these, if not all of them, can be true for certain functions. If we were to look at something like, let's just say we looked at x cubed, this has an inflection point right here at a equal to 0. And if you took the second derivative of this, right, we would have 6x as a second derivative, something like this. And you can see that f double prime does equal 0 at a. In fact, f prime at a is continuous, right? If you do f prime at a, you're going to get 2x squared. So 2x squared looks something like this. That is also continuous at x equal to a. So both of these are actually true. But that's because we're looking at these like nice functions, polynomial ones. We have to look at functions that have inflection points that are more interesting or more unusual. And that actually happens if we took the inverse of this function, the square root. Looks something like this. Goes vertical for a moment, and then looks like that. This does, in fact, have an inflection point right here at a equal to 0. And this is concave up on this side, concave down here. Now, if you look at the second derivative, well, this is the square root of, or the cube root of x. Really, this would also work for the 5th root, 7th root, and all those things. But if you took the second derivative, this is the same thing as x to the 1/3 power. Taking the derivative of this, it's going to give us 1/3 x to the negative 2/3, which gives us 1/3x to the 2/3. So f double prime at a equals 0. Well, if you took the second derivative of this, we would get, let's see, we do 2/3 down. That's going to be, or it's just really 2/3 down here like this. It's going to be, let me just write it out. Bring on, think of 2/3 is going to be a negative 2/9, and then x to the negative 5/3. So going to be x to the negative to the 5/3 on bottom. And f double prime at 0, well, we can't plug 0 into there because we have a division by 0. So this can't be true. F prime at a is continuous. Well, that's not true, right? F prime at a, f prime at 0 is discontinuous. It's a division by 0, so that can't be true. F prime at a has a local extremum. That means the second derivative is equal to 0 at x equal to a, but we've already established that can't happen, so C can't be true. Now D, f has a tangent line at x equal to a. The tangent line here is just the vertical line, but that's true. And in fact, it seems like most inflection points, there should be a tangent line at that point. Like if you were to think of, x squared, or sorry, x cubed has a tangent line of straight across. Any polynomial function at the inflection point is going to have some tangent line at that point. But let's look at E. Double prime is less than 0 for x less than a. This is saying that it has to be, the second derivative has to be less than 0 for anything less than a. And I don't know why you'd ever need that to be the case. Like if you just flip the function, you would just have the opposite side of this. So I don't know why you'd ever need to be less than 0. So I'm sure E can't be true. So D has to be true.